Hello everyone. In this video we will continue to examine topic 7.1, discrete energy and radioactivity, and begin to understand what is known as the Segre plot. So, the Segre plot is a famous type of plot that you should get used to using or viewing. You may have seen it in chemistry. And this plot shows different isotopes, more specifically, I should say different nuclides, and their stability. And it does so by plotting the atomic or proton number on that horizontal axis, and then either the neutron number or the nucleon/mass number on that vertical axis. And I will say you need to be careful about which it is. Because although they imply the same information, the shape on the actual chart will look different. So be a little bit careful. All right. And what you will see is that on a chart that is sort of fleshed out, there is a line of stable isotopes or stable nuclides. Those are shown here by that black staircase-looking thing. Those are nuclides where if that nuclide exists, it tends to be very stable. It tends not to decay, or at least have a very, 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 very long time until it does. Other nuclides that are plotted exist and have been made or formed or detected, but are unstable. Okay. Now you'll notice there are a couple of properties of these stable elements, and I'm point out their properties, and then we'll go about sort of describing what else can be seen from this graph. This is a very famous and important plot or chart. The first is that the stable nuclides start out kind of along this n equals z axis. And the n equals z axis here would mean that a particular stable element would have the same number of protons and neutrons. This is very common for very small elements. Elements like carbon, which has 6 protons and 6 neutrons in its most stable state, would lie along this line. So would helium, with its 2 protons and 2 neutrons. But as you increase in atomic number, you will see that that line of stability bends upwards. So it bends upwards like this above the n equals z line. This means that as you increase in atomic number, you need more and more neutrons compared to the number of protons in order to remain stable. Okay, so you need an increased number of neutrons compared to the number of protons to remain stable. As it turns out, there is sort of a last stable isotope. If you get too big as a nuclide, you are also unstable. Lead-82, lead with atomic number 82 is the last stable isotope that one can make. This is part of why you've heard of it, why it has such notable properties, actually. It is the heaviest stable isotope that we can put to good use. Notice there are many other isotopes that can be made for a variety of times, from pretty long, so a relatively long-lasting nuclide, to nanoseconds. So made in a lab, but not seen otherwise. And if you make them in a lab, you find that they are so unstable they decay very, very quickly. So that's what those would be. The isotopes of a given element can be found by finding the atomic number of that element and then sort of observing the column, the vertical column that corresponds to that atomic number. So you can see that for atomic number of 50 or so, there are actually many possible isotopes. Many possible isotopes to create, although I will say that almost always there are dominant isotopes, isotopes that are significantly more stable than others, but not always. So that's just something to keep in mind. All right. So, first question, why does this bend upwards? Why does the line of stability bend upwards above the n equals z line? That's a really important question. And what is happening is that as z goes up, that is, as you get more and more protons, you need more and more neutrons for the residual strong force to overcome the electrostatic repulsion between the protons. Now, why do you need more and more? It's fundamentally because the electrostatic between the protons, repulsion between the protons, falls off as r squared. So as you get further away and you're building your nucleus, remember these nuclei have many tens and even hundreds of particles. As you get further and further away, they do repel each other less. So protons over here and protons over here will repel each other less. But the residual strong force is incredibly, incredibly sensitive to distance, far more so than the electrostatic repulsion. And the residual strong force basically only glues together the neutrons and the protons that are right next to each other. Any further than that, and it basically has no effect. So as you increase the number of protons, you need more and more neutrons, which don't repel each other, in order to sort of glue the whole nucleus together. That's the key. Now, why don't you just keep adding neutrons? Well, as it turns out, neutrons compared to protons, for reasons that we'll discuss later, are more unstable. So if you can, you'd prefer to have a proton. So to speak, from an energy perspective. That is, neutrons left to their own devices will actually transmute and become a proton plus an electron. A bare neutron, if you manage to sort of isolate a single neutron, would immediately undergo beta decay, and beta minus decay in particular. And so there comes to be a point where in order to bind all the protons together, you would need so many neutrons that those neutrons themselves are not stable enough to sort of hold up. And that's why there's a sort of a ceiling on the stable nuclides. The neutrons also in some ways depend on the protons to keep them stable. So there's sort of a sweet spot of stable nuclei that eventually falls apart if things get too big. Now, the other thing that we can do is we can look at a Segre plot and predict what type of decay a particular particle might undergo based on its location on the Segre plot. And actually for that, I'm going to pause there and we'll tackle it in the next video.